These are the 16 microstates associated with putting 4 particles in one of 2 boxes. We can calculate the number of possible microstates as n raised to the n power, where lowercase n refers to the number of particles and uppercase N is the number of possible boxes to put them in. So 4 squared corresponds to 16 different microstates. When we look at these, we see that A and E are equivalent distributions. This corresponds to 4, 0, and this is 0, 4. Both of these being all the particles in one box. In a similar fashion, B and D are equivalent, as this is 3, 1, and D is 1, 3, i.e. we have 3 particles in one box and just 1 in the second box. And C is a 2, 2 distribution, 2 particles in each box. The highest entropy corresponds to the most probable distribution. So we'll look at A and E. We have a 1/16 plus a 1/16. So this corresponds to a 1/8 of our distributions. B and D correspond to 4 out of 16 plus 4 out of 16, or 1/2 of our total distributions. Finally, C is 6 out of 16, or 3/8 of our total distribution. So our most probable distribution is 3 particles in one box and a single particle in the other box. So this is our highest entropy situation. It corresponds to the distribution that has the highest number of possible microstates. So let's look at this question. We're asked to determine the entropy change if the starting situation was that they were evenly distributed between the 2 boxes, which corresponds to situation C, but on redistribution ended up in box B, which would correspond to distribution C. Boltzmann says that our entropy is going to be equal to the Boltzmann constant of W, where W is the number of microstates. We can write delta S as the final entropy minus the initial entropy. Take advantage of properties of logs. The number of microstates corresponding to the initial state is 6, and the final state is just 1. We can sub in values. K is 1.38 times 10 to the minus 23 joules per K. And then we have ln of 1/6. We get our final answer of negative 2.47 times 10 to the minus 23rd joules per K. Note, we could have expected that delta S would be less than 0 because we are moving to a less probable situation. The second question asks us about the entropy change for a system when it goes from distribution B to distribution D. We see that distribution B and D are equivalent, and they each have 3 particles in one box and 1 in the other box. So we would expect there would be no change in entropy. So we can do the math. Delta S is K ln WF to WI, which is K ln 4 to 4. So that is delta S is equal to 0 as expected. Let's remind ourselves, we go back up here. B and D are equivalent distributions. They're both equally probable, so there's no change in entropy.